4.5 billion years ago, there was no Earth. There was a cloud of gas and dust slowly rotating around a young star, and in that cloud were the atoms that would eventually become this planet. The iron at the center, the silicon in the rock, the oxygen in the air, the water in every cell of every living thing that would one day move across its surface. Those atoms were already ancient when the cloud formed. They had been inside stars, inside supernovae, inside the interstellar medium for billions of years before they drifted together into the disk that would eventually give rise to Earth. And then, slowly, over millions of years, gravity gathered them. The story of Earth is one of the longest, most layered, most patient stories in existence. It is a story of rock becoming ocean, of ocean becoming life, of life becoming atmosphere, of atmosphere becoming the specific breathable miracle that allows everything else. It is a story of catastrophe and recovery, of extinction and renewal, of the same matters cycling through rock and sea and air and biology and back again in loops that have no true beginning and no true end. Every mountain that stands above the horizon tonight is made of material that was once at the bottom of a sea. Every breath of air contains atoms that were once inside a dinosaur, once inside a Cambrian trilobite, once inside the first photosynthetic organism that began the long project of filling the sky with oxygen. Tonight, we are going to travel through that story, gently. Not as a lecture, but as a journey. We are going to start at the beginning, when the Earth was nothing but a violent ball of molten rock in space. And we are going to move forward through deep time at the pace of a quiet night, through the formation of the oceans and the first stirrings of life, through the great oxygenation, through the age of ice and the age of fire, through the slow assembly of the continents and the slow disassembly, through the rise and fall of dynasties of life whose entire existence is now compressed into thin layers of stone, until we arrive here, at this specific planet, tonight, in the particular arrangement of land and sea and atmosphere and life that makes this moment what it is. The room is quiet, the night is long, and the Earth has been waiting 4.6 billion years to be where it is right now. The Earth did not begin gently. The first 100 million years of its history were a period of such sustained and extreme violence that geologists have given that era a name, the Hadean Eon, after the Greek underworld. It was not a metaphor. The early Earth was a world of relentless impact, molten rock, and an atmosphere of steam and carbon dioxide and sulfur compounds that would be unbreathable and uninhabitable by anything alive today. The Earth forms through a process called accretion. In the disk of gas and dust orbiting the young sun, small particles collided and stuck together through electrostatic forces, building pebbles, then boulders, then planetesimals, rocky bodies tens to hundreds of kilometers across, and finally, over millions of years, full-sized planets. Each collision released kinetic energy as heat, and the larger the accumulating body, the more energetic the collisions it experienced as it swept up the remaining material in its orbital neighborhood. By the time Earth had reached something close to its current size, the energy of accretion had melted the entire planet, turning it into a global magma ocean, a sphere of liquid rock, glowing, stirring, radiating heat into space, with no solid surface, no ocean, no atmosphere capable of holding water. Somewhere in this period, the exact timing is still debated, but most evidence points to approximately 4.5 billion years ago, something large struck the early Earth. Astronomers call this object Theia, and it is thought to have been roughly the size of Mars. The impact was not a head-on collision, but a glancing blow, oblique enough to survive as a coherent impact, rather than simply vaporizing both objects instantly, and the result was cataclysmic. Theia's iron core merged with Earth's core, and the outer rocky layers of both bodies were splashed into space in a cloud of vaporized rock, That cloud, orbiting the Earth in a disk of debris, gradually coalesced within perhaps 100 years into the Moon. The Moon began its existence much closer to Earth than it is today, perhaps 20 times closer. Close enough that a hypothetical observer would have seen it filling a significant portion of the sky. The tidal forces between the Earth and Moon were enormous at this distance, generating massive tides and internal heating in both bodies, and gradually, imperceptibly, year by year, across hundreds of millions of years, the Moon has been moving away, transferring angular momentum from Earth's rotation to its own orbit, so that Earth's day has lengthened and the Moon has receded. Today, the Moon is 384,400 kilometers away, and it moves roughly 3.8 centimeters further each year. In the far future, billions of years hence, the Moon will be further still. The period immediately following the giant impact was one of extraordinary geological activity. The Earth, its interior still largely molten, and its surface a cooling crust over a global magma ocean, was bombarded continuously by smaller impactors, the leftover debris of the solar system's formation, still clearing from the inner solar system. Each impact added more heat, kept the surface from consolidating into a permanent solid layer, and delivered additional material, including volatile compounds from the outer solar system. The composition of the Earth's crust and the distribution of elements within it were still being determined during this period by the ongoing accretion and differentiation, the sinking of heavy iron and nickel toward the core, and the floating of lighter silicate minerals toward the surface. The Earth was, in this period, both forming and being destroyed continuously, building its structure from the inside out, while the surface remained too hot and too disrupted for anything resembling the geology we know today. After the giant impact, the Earth began the long process of cooling. The magma ocean surface began to solidify as heat radiated into space, forming the first thin, fragile crust, a dark, basaltic skin over a still liquid interior that cracked and melted and reformed repeatedly as the interior stirred and the crust foundered and remelted. There was no permanent surface in these first hundreds of millions of years. There was only the slow cooling of a planet-sized furnace, the gradual thickening of the crust, and the first hints of the processes that would eventually produce everything else. The oldest known minerals on Earth, zircon crystals found in ancient rocks in Western Australia, have been dated to approximately 4.4 billion years ago. These tiny crystals, barely the size of a grain of sand, survived from the Hadean into the present because of their extraordinary chemical durability. And their isotopic composition tells a story that surprised geologists when it was first decoded. The Hadean Earth may not have been as uniformly hellish as the name implies. The zircon chemistry suggests that liquid water was present on the surface by at least 4.4 billion years ago, within 150 million years of Earth's formation, and possibly even earlier. The planet cooled faster than the violent Hadean narrative suggested, and the oceans, whose formation we think of as a later development, may have appeared remarkably early in the planet's history. The water that fills Earth's oceans today is old. It arrived on a young planet through a delivery process that took hundreds of millions of years and came from multiple sources. And the story of how the oceans formed is one of the more geologically elegant stories in Earth history. Some of Earth's water was present from the beginning, incorporated into the rocky planetesimals that built the planet as hydroxyl groups chemically bound within silicate minerals. As the early Earth melted and differentiated, its iron sinking to the core, its silicate rock floating above, this bound water was released through volcanic outgassing, expelled from the interior as steam that contributed to a thick early atmosphere of water vapor and other gases. As the surface cooled below the boiling point of water, this atmospheric steam condensed and fell as rain for millions of years, filling the low places in the slowly forming crust and becoming the first oceans. Additional water arrived later from beyond the asteroid belt, delivered by water-rich asteroids and comets that bombarded the inner solar system during the period called the Late Heavy Bombardment, approximately 4.1 to 3.8 billion years ago, when the gravitational shuffling of the outer planets sent a rain of rocky and icy material inward. How much of Earth's water came from this late bombardment and how much was outgassed from the interior remains an active area of research, with isotopic analyses of ocean water and asteroid water providing evidence for both sources. The answer is probably a combination of the two, with the specific proportions still being refined. The first ocean was not blue in the way the modern ocean is blue. The early ocean was likely warm, perhaps very warm. Temperatures have been estimated from the chemistry of ancient sedimentary rocks at anywhere from 60 to 80 degrees Celsius in places, and it had a chemistry very different from today's. It was rich in dissolved iron and silica, poor in oxygen, and had a pH that may have been slightly acidic. It was, in short, a different kind of sea, governed by different chemistry, under a different sky. The sky above the early ocean was not blue either. The young sun was approximately 70% as luminous as it is today. The early atmosphere was thick with carbon dioxide and methane, greenhouse gases that compensated for the sun's lower output and kept the surface from freezing. The sky may have been orange or yellowish, tinted by the methane and the particular way light scattered through a denser, differently composed atmosphere. An observer standing on the shore of that early ocean, if any had existed, would have been standing on a world that was recognizably Earth in its basic organization, but alien in almost every sensory detail. The ocean played a central role in shaping early Earth's geology in ways that extend far beyond providing a medium for early life. The presence of liquid water at the surface initiated the processes of weathering and erosion, which broke down the early volcanic rocks and carried the dissolved and particulate products into the sea. The ocean floor spread and subducted, with the oceanic crust being created at mid-ocean ridges and destroyed at subduction zones, in a slow circulation that has continued, with variations, to this day. The water that went down with the subducting oceanic crust into the mantle was released in the melting of the subducting slab, contributing to the volcanic eruptions above subduction zones, and recycling water between the ocean and the deep earth, in a planetary water cycle that operates over millions of years. This deep water cycle, water from the ocean carried into the mantle by subduction and returned to the surface through volcanic activity, is one of the most important long-term stabilizing processes in Earth's history, because it links the ocean's chemistry to the chemistry of the solid Earth and allows feedbacks that have kept the ocean present and the surface habitable for billions of years. Earth has neither dried out nor been overwhelmed with water, because the cycling between the ocean and the mantle has maintained the balance. The ocean is not simply sitting on the surface of the planet. It is circulating through the planet on timescales of hundreds of millions of years, in a slow planetary metabolism that keeps the surface conditions stable enough for the long, patient project of evolution to proceed. The salinity of the modern ocean, approximately 3.5% salt by mass, has been surprisingly stable over the past several hundred million years, maintained by a balance between the addition of salts through weathering and the removal of salts through the formation of evaporite minerals in shallow seas. The composition of seawater has changed over geological time, with varying concentrations of different ions, as the relative rates of volcanic and sedimentary input shifted. But the overall ionic strength has remained in a range compatible with marine life throughout the Phanerozoic era. The ocean has been a stable, persistent chemical environment for the organisms that have lived in it, not unchanging, but changing slowly enough that life has always had time to adapt, and in adapting, to modify the ocean chemistry in ways that stabilized it further. The ocean and life have been managing each other for billions of years, each shaping the other's chemistry in a feedback loop that has maintained both. Somewhere between 3.7 and 4 billion years ago, the exact moment and place are not known, something happened on Earth that had never happened anywhere in the universe before, as far as we know. A chemical system assembled itself that could copy itself. A molecule or a collection of molecules in a membrane or a reaction cycle in a mineral pore crossed the line from chemistry to biology. The first life left no fossils of the kind we would recognize. It was too small, too soft, and too simple to leave the structural imprints in rock that paleontologists study. What it left instead were chemical and isotopic signatures in some of the oldest rocks on Earth. Carbon isotope ratios in ancient Greenland and Western Australian rocks that bear the distinctive signature of biological carbon processing, the same bias toward lighter carbon isotopes that all life produces when it processes carbon through metabolic reactions. These chemical whispers from 3.7 to 4 billion years ago are the earliest evidence of life, and they are contested. Not all geologists agree that the signatures are unambiguously biological rather than abiotic, but they represent the frontier of what the record currently shows. The oldest unambiguous fossils are stromatolites, layered structures built by microbial communities that trapped and cemented sediment particles in thin layers, producing dome-shaped or columnar structures that could be preserved in rock. Fossil stromatolites from the Pilbara region of Western Australia have been dated to approximately 3.5 billion years ago, making them the clearest early evidence of life that survives in the rock record. Living stromatolites still exist today, in a few locations around the world, where conditions replicate those that allowed them to flourish 3.5 billion years ago. Most famously in Shark Bay in Western Australia, where the shallow, hypersaline waters create an environment too challenging for most organisms that would otherwise graze on the microbial mats. To stand at the edge of Shark Bay and look at those living stromatolites is to look at a community of organisms whose basic design has been maintained since a time when the Earth's entire continental landmass was organized entirely differently, and nothing more complex than a bacterium existed anywhere. The first life was almost certainly microbial, single-celled organisms without a nucleus, what biologists call prokaryotes, whose descendants are still with us today in the form of bacteria and archaea. These organisms were, by every subsequent standard of biological complexity, simple, but they were metabolically extraordinarily diverse, having developed over billions of years a range of chemical strategies for extracting energy from the environment that collectively cover nearly every thermodynamically feasible energy gradient available in the natural world. Bacteria can live on sulfur, on iron, on hydrogen, on light, on organic compounds, on carbon monoxide, on ammonia. They can live in the dark, in the cold, in boiling water, in concentrated acid, in salt concentrations that would crystallize the contents of any other cell. Life, having established itself, proved extraordinarily difficult to eliminate and extraordinarily inventive in finding new ways to persist in any environment the Earth could provide. One of the most significant transitions in the history of life on Earth was the origin of the eukaryotic cell, the kind of cell that makes up every plant, animal, fungus, and protozoan alive today. The eukaryotic cell is dramatically more complex than a prokaryotic cell, with a nucleus containing the DNA, a system of internal membranes dividing the cell into functional compartments, and, most remarkably, organelles called mitochondria that are the cell's energy-generating powerhouses. The mitochondria are so structurally and genetically similar to bacteria that the leading theory of their origin, the endosymbiotic theory, proposed by Lynn Margulis in 1967, holds that they are former bacteria that were engulfed by a larger host cell approximately 2 billion years ago, and rather than being digested, formed a stable symbiotic relationship in which the engulfed bacterium provided energy-generating services in exchange for protection and nutrients. All the mitochondria in all the cells of your body are the descendants of that ancient bacterial partnership. Every breath you take is powered by the biochemical machinery of what was once a free-living bacterium. The emergence of photosynthesis, the ability to capture the energy of sunlight and use it to build organic molecules from carbon dioxide, was the single most transformative metabolic innovation in Earth's history. And it happened in bacteria approximately 3.5 to 3 billion years ago. The specific form of photosynthesis that would change the world, oxygenic photosynthesis, which uses water as an electron donor and releases oxygen as a waste product, evolved in the cyanobacteria. And its appearance set in motion the most dramatic single chemical change in Earth's atmospheric history. The Great Oxygenation Event. For the first 2 billion years of Earth's history, the atmosphere contained almost no free oxygen. This is not a subtle absence. It is the defining chemical characteristic of the early Earth that makes it alien to everything alive today that depends on oxygen for respiration. The early atmosphere was reducing rather than oxidizing, dominated by nitrogen, carbon dioxide, methane, and water vapor, with no oxygen in the free molecular form that powers the metabolism of every animal on Earth. The cyanobacteria changed this. For hundreds of millions of years, cyanobacteria had been releasing oxygen as a metabolic byproduct into the ocean. But the ocean had absorbed it. Iron dissolved in the seawater reacted with the oxygen, precipitating it out as iron oxide, the banded iron formations that we now mine as iron ore, and that represent the chemical record of this ancient oxygen absorption. For as long as the ocean had free iron to react with, the oxygen released by photosynthesizing cyanobacteria was captured before it could accumulate in the atmosphere. But around 2.4 billion years ago, the ocean's capacity to absorb oxygen was exhausted. The dissolved iron had been depleted, and the oxygen, continuing to be produced by the photosynthesizing cyanobacteria in ever greater quantities as they spread across the sunlit ocean surface, began to accumulate in the atmosphere. This was the Great Oxygenation Event, and it was catastrophic for most of the life that existed at the time. Oxygen, the molecule we breathe and depend on, is chemically reactive in ways that make it toxic to organisms that have not evolved defenses against it. The early life that inhabited the oxygen-free early Earth had no such defenses. For those organisms, the anaerobes, the Great Oxygenation Event was a mass extinction of the most total kind, an atmospheric poisoning on a planetary scale. The oxygen-sensitive anaerobes retreated to the sediment, to the deep ocean, to the anoxic environments where oxygen still could not penetrate. And the survivors of this catastrophe are the ancestors of the anaerobic bacteria that still live in those same refugia today. For the story of what would eventually become complex life, the Great Oxygenation Event was the necessary precondition. Oxygen allows a form of metabolism, aerobic respiration, that extracts far more energy per molecule of glucose than the anaerobic alternatives. An organism that can respire aerobically has access to roughly 16 times more energy per unit of food than an anaerobe. This energy surplus was what eventually made possible the complexity of eukaryotic cells, and eventually the complexity of multicellular animals. The air you are breathing tonight is the legacy of 2.5 billion years of cyanobacterial photosynthesis. Every breath is a debt to an organism that looked, and still looks, like a tiny blue-green filament, with no nucleus, no organelles, no complexity that a casual observer would find impressive, but which changed the chemistry of an entire planet and made everything that came after possible. The oxygen in the atmosphere also had another consequence. It was converted by ultraviolet radiation in the upper atmosphere into ozone, building the ozone layer that filters out the most damaging wavelengths of UV radiation from the sun. The ozone layer did not exist before the Great Oxygenation event. Its formation was a gradual process, taking hundreds of millions of years to build up sufficient ozone to provide meaningful UV shielding. But when it was sufficiently established, it opened the sunlit surface of the land and the shallow ocean to life that had previously been confined to depths where UV radiation could not penetrate, setting the stage for the eventual colonization of land. The colonization of land by life, beginning approximately 500 million years ago with algae and fungi, and eventually producing the first vascular land plants around 425 million years ago, was another transformation as profound as the Great Oxygenation in its long-term consequences. Bare rock and sand had covered the continental surfaces for the first 4 billion years of Earth's history, periodically scoured by wind and rain, but otherwise biologically inert. The arrival of land plants changed everything about the way the continents functioned. Plant roots chemically weathered rock at an accelerated rate, releasing minerals that washed into rivers and eventually the ocean. Decaying plant matter built up in the soil, creating the organic rich substrate in which future generations of plants could grow more productively. The evapotranspiration of land plants began to move water from the soil back into the atmosphere, contributing to the development of rainfall patterns over continental interiors that had previously been deserts. The first forests, which appeared during the Devonian period, approximately 385 million years ago, covered vast areas of the tropical Pangaean landmass and drew so much CO2 from the atmosphere through photosynthesis that global temperatures dropped significantly, contributing to a glaciation that left ice sheets at the poles during a period when the equatorial climate was otherwise warm. Life was changing the planet's climate hundreds of millions of years before any human existed to observe it. The cyanobacteria that started all of this, the organisms whose oxygen-producing photosynthesis set in motion the Great Oxygenation event and ultimately made complex life possible, are still here. They still live in the sunlit surface waters of every ocean. They still fix CO2 into organic matter through the same biochemical pathways they evolved 3 billion years ago. They have been photosynthesizing through every extinction event, every ice age, every supercontinent assembly and breakup, every mass extinction that wiped out most other species on Earth. The cyanobacteria that made your atmosphere are still making it, tonight, in the ocean you cannot see from where you are lying, but that is there, under the dark sky, doing what it has always done. There is a concept in geology called deep time, coined by the writer John McPhee in his book about geology, and it refers to the temporal scale on which geological processes operate, a scale so far beyond ordinary human experience that it requires a deliberate act of imagination to begin to grasp it. The age of the universe is 13.8 billion years. The age of Earth is 4.6 billion years. The time since the Cambrian explosion, when complex multicellular animals first appeared in the fossil record, is 538 million years. The time since the dinosaurs went extinct is 66 million years. The time since the first anatomically modern humans walked in Africa is approximately 300,000 years. Laid out in these numbers, the proportions are striking. If the entire history of Earth were compressed into a single calendar year, with the formation of the planet on January 1st, complex multicellular animals would not appear until late November. The dinosaurs would go extinct on December 26th. Humans would appear in the last few hours of December 31st. The entire span of recorded human history, from the first writing to the present day, would occupy the last minute and a half of the year. This compression is not intended to make humanity feel small. It is intended to make the patience of geological processes feel real. A mountain range is built over tens of millions of years by the slow collision of tectonic plates, squeezed upward by forces too gradual to perceive, but too immense to resist. The Himalayas, the highest mountains on Earth, began forming when the Indian subcontinent, moving northward at a few centimeters per year, began colliding with the Eurasian plate approximately 50 million years ago. In deep time terms, a geologically recent event. The mountains are still rising. The collision is still happening. India is still moving north at roughly 5 centimeters per year, the same speed at which a human fingernail grows. The rocks beneath your feet, wherever you are tonight, contain a history of deep time encoded in their minerals, their crystal structures, their isotopic compositions, and their layering. A piece of granite contains zircon crystals that formed when the granite crystallized from magma. And those crystals contain radioactive uranium that decays at a known rate into lead, a clock that has been running since the granite formed, and that geologists can read to determine how long ago the rock solidified. A piece of limestone contains the compressed shells of marine organisms that lived in a warm, shallow sea tens or hundreds of millions of years ago, far from any ocean that exists today. The stone is a record, written in chemistry and crystal, of every environment the Earth has moved through in the long patience of its history. The Cambrian explosion, 538 million years ago, represents one of the most dramatic entries in the rock record, the sudden, geologically rapid appearance of diverse, complex, multicellular animal life with hard shells and skeletons that could be preserved as fossils. Before the Cambrian, the animal fossil record is sparse and largely soft-bodied. After it, almost every major animal body plan, the basic architectural blueprints for worms, mollusks, echinoderms, arthropods, and our own chordate ancestors, appears in the rock record within a span of perhaps 20 to 30 million years. This apparent explosion of form has been interpreted in various ways, as a genuine rapid evolutionary diversification driven by ecological opportunity and evolutionary innovation, as the result of a threshold in body complexity being crossed that suddenly allowed skeletonization and therefore preservation. Whatever caused it, the Cambrian explosion produced the biological diversity that, by subsequent modification and extinction and radiation, eventually led to every complex animal alive today. The history of life since the Cambrian has been punctuated by 5 major mass extinctions, events in which a significant fraction of Earth's species disappeared within a geologically short time. The largest of these, the Permian-Triassic extinction, approximately 252 million years ago, eliminated perhaps 90 to 96% of all marine species and 70% of all terrestrial vertebrate species. The closest life has come to complete extinction in the last 500 million years. The cause was almost certainly the massive volcanic eruptions of the Siberian Traps, a flood basalt event that released enormous quantities of CO2 and other gases over perhaps 1 million years, warming the climate, acidifying the ocean, and creating the conditions for a cascading ecological collapse. Life recovered, as it has from every previous extinction, but the recovery took tens of millions of years, and the world that emerged from the Permian extinction was fundamentally different from the one that had entered it. The most famous mass extinction, the Cretaceous-Paleogene extinction, 66 million years ago, that ended the non-avian dinosaurs, was caused by the impact of an asteroid approximately 10 kilometers in diameter near the Yucatan Peninsula of Mexico, producing an impact crater 180 kilometers across, triggering wildfires across much of the planet, injecting enormous quantities of dust and soot into the stratosphere, and reducing sunlight at the surface for months to years. 3/4 of all species on Earth went extinct. But among the survivors were the small feathered dinosaurs, the birds, and the small mammals who had lived in the shadow of the dinosaurs for 165 million years, waiting for an opportunity that arrived in a geological instant. The extinction of the dinosaurs was the opening that allowed mammals to diversify and eventually 66 million years later, to produce the species that is lying in bed tonight, reading the story of the planet it lives on. The rock cycle is one of the most beautiful processes in Earth science, and it is one of the most comforting. Rock is not permanent. It only seems permanent on human timescales. On geological timescales, rock is as fluid as water, cycling between the surface and the interior, between igneous and sedimentary and metamorphic forms, between ocean floor and mountain peak, in a cycle with no beginning and no end. The atoms that are currently locked in granite will eventually, over hundreds of millions of years, be released by weathering, carried to the sea, deposited as sediment, buried by more sediment, subjected to heat and pressure in the depths of the earth, and eventually melted back into magma or metamorphosed into new rock. Nothing in the rock record is permanent. Everything is in the process of becoming something else, at a pace that makes the word slow seem inadequate. The Earth's climate has never been static. Across its 4.6 billion-year history, the planet has moved through periods of warmth so extreme that there was essentially no ice at the poles, and periods of cold so intense that glaciers reached to the equator, a condition geologists call snowball Earth, at least twice in the Precambrian. The carbon dioxide concentration in the atmosphere has ranged from values many times higher than today to values so low that plants struggle to photosynthesize efficiently. Sea levels have risen and fallen by hundreds of meters as ice sheets grew and melted, and the thermal expansion and contraction of the ocean water responded to temperature change. The climate of Earth is not a stable background condition. It is a dynamic system that has been continuously changing, sometimes gradually and sometimes catastrophically, throughout the planet's history. The Snowball Earth episodes, occurring approximately 720 and 635 million years ago, are among the most dramatic climate events in the geological record. During these episodes, the geological evidence suggests that ice covered the ocean from pole to equator, with global mean temperatures dropping to perhaps minus 50 degrees Celsius. The mechanism that ended each Snowball Earth episode involves the continued outgassing of carbon dioxide by volcanoes, which continue to operate beneath the ice, gradually building up atmospheric CO2 until the greenhouse warming was sufficient to melt the ice, triggering a rapid and dramatic warming. The aftermath of the Snowball Earth episodes was a period of intense chemical weathering as the newly exposed rocks reacted with the CO2-rich atmosphere, eventually drawing the carbon dioxide back down and restoring something closer to equilibrium conditions. There is a hypothesis, still debated but widely considered plausible, that the Snowball Earth episodes played a role in the evolution of complex life. The extreme environmental stress of the global glaciation and the dramatic environmental shifts of the aftermath may have driven evolutionary experimentation and diversification in the microbial communities that survived beneath the ice, contributing to the evolutionary changes that eventually produced the complex multicellular organisms of the Cambrian explosion. The Cambrian explosion, the geologically rapid appearance in the fossil record of most of the major animal body plans, occurred approximately 538 million years ago, not long after the last Snowball Earth episode. Whether the two events are causally connected remains an open question, but the coincidence is suggestive. The ice ages of the more recent geological past, the Quaternary glaciations, which began approximately 2.6 million years ago and have produced dozens of cycles of glacial advance and retreat, were driven by a different mechanism, the Milankovitch cycles, periodic variations in Earth's orbit and axial tilt that change the distribution of solar radiation over the Earth's surface and trigger the growth or melting of ice sheets over cycles of tens of thousands of years. The most recent glacial maximum was approximately 20,000 years ago, when ice sheets covered most of Canada and northern Europe to depths of several kilometers. Sea levels were approximately 120 meters lower than today, because enormous quantities of water were locked in the ice. The English Channel was dry land. Australia, New Guinea, and Tasmania were a single landmass. The Bering Land Bridge connected Asia and North America, and the first humans to reach the Americas walked across it. As the ice melted over the following 10,000 years, the sea level rose, drowning the coastal plains and river valleys, and creating the geography of coastlines we know today. The Thames estuary filled with water. The Persian Gulf flooded. The Black Sea, which had been a freshwater lake isolated from the Mediterranean, was inundated when rising sea levels breached the land barrier at the Bosphorus, filling it with salt water in what may have been a rapid and dramatic flood event. The world that humans first built their civilizations in was a world shaped by the aftermath of the last ice age, its coastlines and rivers and agricultural valleys, all products of the particular climatic conditions that followed the glacial maximum. One of the most disorienting realizations available to anyone who studies Earth history is that the land beneath our feet is not where it has always been. The continents move, not metaphorically, but literally, traveling across the surface of the planet at rates measured in centimeters per year, but amounting to thousands of kilometers over geological time. The configuration of land and ocean that we consider the natural state of the world, the Americas on one side, Europe and Africa on the other, Asia and Australia in between, is a temporary arrangement, one of many that have existed over Earth's history. And the continents are currently in the middle of another slow rearrangement that will produce a completely different map of the world in another 100 million years. The theory of plate tectonics, which explains how and why the continents move, was not accepted by mainstream geology until the 1960s, even though the basic idea that the continents were once joined and have drifted apart was proposed by Alfred Wegener in 1912. Wegener's evidence for continental drift was straightforward and compelling. The shapes of the continents fit together like puzzle pieces, most obviously South America and Africa. The rocks on matching continental margins had the same types and ages. The fossil record showed the same species on continents now separated by thousands of kilometers of ocean. But without a mechanism to explain how the enormous masses of the continents could be moved, the geological establishment was resistant, and Wegener was largely dismissed during his lifetime. The mechanism was ocean floor spreading, discovered in the 1950s and 1960s through the mapping of the seafloor and the measurement of its magnetic properties. New oceanic crust is created continuously at mid-ocean ridges, where magma rises from the mantle and solidifies. And old oceanic crust is destroyed at subduction zones, where it dives beneath the lighter continental crust and is reabsorbed into the mantle. The ocean floor is a conveyor belt, carrying the continents on the backs of the moving tectonic plates as new crust pushes outward from the ridges and old crust sinks at the margins. The Atlantic Ocean is widening at roughly 2.5 centimeters per year. The Pacific is narrowing. The Indian subcontinent is still moving northward into Asia, producing the Himalayas. California's San Andreas Fault, where the Pacific plate slides northward past the North American plate, moves roughly 5 centimeters per year on average, accumulated in sudden lurches that produce earthquakes. 300 million years ago, the continents were assembled into a single supercontinent called Pangaea. All the world's land in one enormous landmass, surrounded by a single global ocean called Panthalassa. Before Pangaea, there were other supercontinents, Rodinia, 1 billion years ago, and Nuna before that. The cycle of supercontinent assembly and breakup, driven by the internal heat of the Earth and the circulation of the mantle, appears to operate on a period of roughly 500 to 600 million years. If the cycle continues, the continents currently drifting apart will eventually begin to reassemble. Geologists have modeled the future supercontinent, sometimes called Pangaea Proxima or Amasia, which is projected to form approximately 250 to 300 million years from now, as the Atlantic Ocean closes and the Americas collide with Europe and Africa. The breaking up of Pangaea 200 million years ago was directly relevant to the evolution of life in ways that are still visible in the modern distribution of species. When Pangaea was intact, animals and plants could walk or spread across a single landmass. As the continents separated, populations were divided by growing oceans, and the separated populations evolved independently, producing the biogeographic patterns: why marsupials are in Australia, why lemurs are only in Madagascar, that puzzled naturalists for centuries before plate tectonics provided the explanation. The map of life on Earth today is, in large part, a map of where the continents have been and how they have moved. The collision of India with Asia, which began approximately 50 million years ago and produced the Himalayas, is itself a story of geological patience in action. The Indian subcontinent was once part of the southern supercontinent Gondwana, positioned far to the south of its current location. When Gondwana began to break apart roughly 180 million years ago, India separated from Antarctica and Africa and began drifting northward, accelerating to speeds of up to 20 centimeters per year, unusually fast for a tectonic plate, before colliding with the Eurasian plate. The collision has not stopped. India is still moving north, and the Himalayas are still being pushed upward by the ongoing compression of the crust. The summit of Mount Everest, the highest point on Earth's surface at 8,849 meters above sea level, is made of limestone, marine sedimentary rock laid down at the bottom of an ancient sea called the Tethys Ocean, which was consumed when India plowed northward and closed it. The highest place on the land surface of Earth was once ocean floor. The Wilson cycle, named after geologist Tuzo Wilson, who helped develop the theory of plate tectonics, describes the complete life cycle of an ocean basin, from the initial rifting of a continent through the spreading and widening of the ocean to the eventual closing and collision as the ocean floor subducts and the continents on either side are brought together. The Atlantic Ocean is currently in the spreading phase of a Wilson cycle that began approximately 175 million years ago when North America and Europe began separating. At some future point, geologists project, subduction zones will develop at the Atlantic margins. The ocean will begin to close, and the cycle will eventually conclude with a continental collision, the assembly of whatever the next supercontinent will be. The cycle has no end because it has no beginning. It has been operating, in some form, since the Earth first developed a rigid outer shell and a convecting mantle, perhaps 3 billion years ago or more. The continents are not drifting aimlessly. They are following the long, patient logic of planetary heat loss, cycling through configurations that geologists can read in the rock record and project forward into the deep future. Earth is the only planet we know of with life, and the most remarkable aspect of life on Earth, beyond its mere existence, is how thoroughly it has transformed the planet it lives on. Life is not a passenger on Earth, adapted to the conditions the planet provides, and leaving those conditions otherwise unchanged. Life is a geological force, reshaping the atmosphere, the ocean chemistry, the rock cycle, and the climate over billions of years in ways that have created the conditions for more and more complex life to arise. The oxygen in the atmosphere is the most dramatic example, but it is not the only one. The carbonate rocks, limestones, and chalk and dolomites that form such a significant part of the sedimentary record are largely biological in origin, precipitated from seawater by marine organisms building shells and skeletons that accumulated on the seafloor over hundreds of millions of years and were compressed into rock. The White Cliffs of Dover are made of the compressed shells of microscopic marine algae called coccolithophores that lived in a warm, shallow sea approximately 70 to 100 million years ago. The chalk is life. The landscape is life compressed into stone. The coal and oil and natural gas that human civilization has been burning for the past 2 centuries are the compressed, and chemically transformed remains of biological material. Forests that grew during the Carboniferous period, 300 to 360 million years ago, in the swamps and lowlands of a tropical Pangaea, whose wood resisted decomposition because the fungi and bacteria that today break down lignin had not yet fully evolved the enzymes to do so. For tens of millions of years, wood accumulated in the swamp sediments rather than rotting, building up the enormous organic deposits that we call coal. The energy that comes from burning coal is solar energy captured by photosynthesis 300 million years ago and stored in the chemical bonds of that ancient vegetation. The soil beneath every field and forest is another product of life, a complex mixture of mineral particles, organic matter, water, air, and an extraordinary density of living organisms. A single teaspoon of healthy soil may contain more bacteria than there are humans on Earth, along with thousands of species of fungi, protists, nematodes, mites, and other organisms interacting in a web of nutrient cycling and chemical transformation that makes the soil the foundation of terrestrial life. The fertile soil of the productive farmland is not simply ground-up rock. It is a living system built by biological activity over thousands of years that takes the mineral raw material of geological weathering and transforms it into the medium in which plants can grow and food webs can function. The planet we inhabit tonight is not the planet that formed 4.6 billion years ago. It is a planet that has been profoundly, irreversibly transformed by life, by the metabolic activity of billions of years of organisms breathing and photosynthesizing and dying and decomposing and building shells and burrowing and erupting in evolutionary novelty and going extinct and being replaced and cycling the same atoms through the same processes in the same ocean and atmosphere with a patience that makes all of human history look like a recent footnote. The extent to which life has modified the solid Earth beyond the atmosphere and ocean chemistry is still being appreciated by geologists and biologists working at the intersection of the two disciplines. Burrowing organisms transformed the sediment record starting in the Cambrian, mixing and oxygenating seafloor sediments in ways that changed the chemistry of the ocean floor. Vascular land plants, which evolved approximately 425 million years ago and spread across the previously barren continental surfaces, transformed the weathering rate of silicate rocks by sending roots into rock fractures, accelerating the chemical breakdown of minerals, and drawing carbon dioxide from the atmosphere into the rock as calcium carbonate, contributing to the dramatic decrease in atmospheric CO2 that occurred during the Carboniferous period and helping to cool the climate of that era. The evolution of trees and forests created the ecological infrastructure for the terrestrial food webs that would eventually support the animals that colonize the land. The fungi deserve particular recognition in the story of Earth's transformation by life. Fungi are the planet's primary decomposers, breaking down the complex organic polymers, cellulose, lignin, chitin, that plants and animals produce and that would otherwise accumulate as dead matter rather than being recycled back into the nutrient cycles. Before the evolution of lignin-degrading fungi in the Carboniferous, the structural material of dead wood accumulated in swamps for millions of years rather than decomposing, contributing to the formation of coal. The evolution of white rot fungi that could break down lignin essentially ended the geological accumulation of wood-based coal. Fungi also form mycorrhizal associations with approximately 90% of all land plant species, extending the plant's root systems through the soil in exchange for photosynthetically fixed carbon. A symbiosis so ancient and so universal that land plants may never have been able to colonize terrestrial environments without fungal partners. The ocean today, sustained by the same biological processes that have operated for billions of years, is one of the most productive systems on Earth. Phytoplankton, microscopic photosynthetic organisms drifting in the sunlit surface waters, produce approximately half of all the oxygen in Earth's atmosphere through photosynthesis. These invisible organisms, too small to see individually with the naked eye, are the foundation of the marine food web that sustains everything from krill to whales, and they play a central role in the global carbon cycle by fixing CO2 into organic matter that sinks to the seafloor when the phytoplankton die, removing carbon from the atmosphere and the surface ocean, and sequestering it in the deep. This biological pump, as oceanographers call it, has been operating for billions of years and is one of the most important carbon sinks in the global carbon cycle. And yet, here we are, at the end of that long story, in a body made of the atoms that have been through all of it, breathing the air that life made, drinking the water that the ocean cycle has been purifying and redistributing for billions of years, living on a planet that has been warmed by the same star since before any of the molecules in our cells existed. The story of Earth is the story of the room you are lying in tonight, and the story of you. Right now, tonight, on the planet you are lying on, somewhere in the deep ocean, hydrothermal vents are erupting mineral-rich water into the cold sea, supporting dense communities of organisms that have never seen sunlight, living on the chemical energy of the Earth's interior, exactly as their ancestors did before the first photosynthetic organism evolved. The conditions at those vents are very similar to conditions in the early ocean, and some of the organisms that live there are among the most ancient lineages of life on Earth, living windows into the Hadean. In the Mariana Trench, 11 kilometers below the ocean surface, bacteria and amphipods and snailfish are going about their lives in the deepest point on the planet's surface, under pressures that would crush a submarine, in water barely above freezing, in a world of permanent darkness, broken only by the occasional bioluminescent flash of a passing animal. In the Amazon basin, the largest rainforest on Earth is cycling carbon through its trees and soil and rivers at a rate that makes it a significant regulator of the global carbon cycle, drawing billions of tons of CO2 from the atmosphere each year for the photosynthesis of its billions of trees. The forest is so large that it generates its own rainfall, the trees transpiring water vapor that forms clouds that fall as rain further inland. A self-sustaining water cycle within a water cycle. The Amazon River alone carries approximately 20% of all the fresh water that flows into the ocean from all the world's rivers combined, draining a basin larger than the contiguous United States and representing in its volume and its biological richness a concentration of planetary vitality with few equivalents anywhere on Earth. In the Arctic and Antarctic, ice sheets that have accumulated over hundreds of thousands of years are recording the chemistry of every year's atmosphere in the bubbles of ancient air trapped in the ice. A frozen archive of Earth's climate history, readable in ice cores extracted by drills that descend hundreds of meters into the ancient ice. Those ice cores contain air from before humans began burning fossil fuels, air from the medieval warm period, air from the last ice age, air from every century of the Holocene, each layer sealed and preserved by the slow accumulation of snowfall year by year. The Dome Sea ice core from Antarctica contains a continuous record of atmospheric composition stretching back 800,000 years. 800,000 years of annual layers, each one preserving a sample of the atmosphere from the year that snowfall was deposited. A library of planetary chemistry that no other archive can match. In mid-ocean ridges, new oceanic crust is being created tonight, as it has been every night for billions of years, as basaltic magma rises from the mantle, splits the seafloor apart, and solidifies into the fresh, dark rock that forms the foundation of the ocean floor, and begins its long, slow journey toward the subduction zones at the ocean margins, where it will eventually descend back into the mantle and be reabsorbed. Somewhere, tonight, a volcano is erupting, releasing gases from the deep earth into the atmosphere, adding to the small but continuous contribution of volcanic outgassing that has been maintaining the atmosphere's composition for billions of years, cycling carbon and sulfur and water between the interior and the surface in the planetary metabolism that has kept conditions habitable through all the changes of deep time. And above all of it, the atmosphere is doing what it has always done, absorbing incoming solar radiation, redistributing heat from the equator toward the poles in vast, slow circulations of air that we call weather, allowing the planet to maintain the moderate temperature gradients that drive the wind and the rain and the cycles of evaporation and precipitation that move water through the landscape and deliver it to the rivers and the soil and the roots of the trees and the cells of every living thing. The jet stream is flowing tonight, miles above where you are lying, guiding weather systems around the hemisphere in its characteristic meandering path, steering storms and calms and fronts and the slow progression of seasons from winter to spring to summer to autumn and back again. The ocean currents are moving tonight, the Gulf Stream carrying warm tropical water northward along the American coast and across to Europe, moderating the climate of the British Isles and Scandinavia in ways that make those latitudes far warmer than they would otherwise be. The deep ocean is circulating in its thermohaline conveyor, cold, dense water sinking in the North Atlantic and flowing slowly southward and then around the globe in a circulation pattern that takes roughly 1,000 years to complete, and that distributes heat and nutrients across every ocean basin on the planet. The Earth is not finished. It is in full operation tonight, as it has been for 4.6 billion years, running the geological and biological and atmospheric and oceanic processes that have made it what it is. Every system is interconnected with every other. The rock cycle feeds the ocean chemistry, feeds the atmosphere, feeds the climate, feeds the life, feeds the rock cycle again. The planet is a loop, not a line, a self-regulating system of extraordinary complexity and extraordinary resilience, built over billions of years of trial and error and catastrophe and recovery. Still learning, still changing, still cycling. The room you are lying in is built from materials this planet assembled. The air in your lungs was made by organisms this planet evolved. The water in your blood was once in the ocean, once in the ice, once in the clouds, once in the roots of trees and forests that no longer exist. You are made of Earth, breathing Earth's air, warmed by Earth's sun, resting on Earth's surface. You are not separate from this 4.5 billion year story. You are the current expression of it, the latest in a long, unbroken chain of living things on a living planet, each one a small participant in the endless cycling of matter and energy that this extraordinary world has been conducting since before complex life existed. The Earth will continue long after tonight. The volcanoes will erupt, the continents will drift, the ocean will cycle its water through the rock and back again. The cyanobacteria will photosynthesize in every sunlit corner of every ocean as they have for 3.5 billion years. The stars will rise and set over the same planet that watched them rise and set, when nothing more complex than a bacterium existed on its surface. And tonight, on this specific point of this specific planet, the night is quiet. The air is warm enough. The weight of you against the bed is the weight of the Earth holding you, as it has held everything that has ever lived on it, in the patient, certain grip of its gravity. Rest now. The story has been going for 4.6 billion years and is nowhere near its end. Tonight is just one night in it, one quiet, ordinary, extraordinary night on a living planet.